Okay, so the three laws of motion that we just talked about in the previous video, video 24, Newton's three laws of motion were published in 1687 in the Principia, and they made a lot of sense to a lot of people. Not only were they right, I mean, not only did they produce good results, and not only were they consistent with experiment, okay, but they kind of made intuitive sense, like you could sort of see what was happening with them, okay. Inertia was an idea that just really, really clicked once people saw it. It just took once you saw it, it made a lot of sense. It was kind of intuitive once you got a hold of it. But the fourth law that showed up in the Principia, okay, violated common sense completely. Okay, that law was the law of gravity. What Newton called universal gravitation. We'll see later why it was called universal. Nothing to do with the universe, but having to do with the fact that it applies everywhere. It's universal. Universal gravity. This was an idea which really surprised people. Here is gravity in a nutshell. If you want gravity in a single simple sentence, it's this. Every object attracts every other object. That's it. That's gravity. Now, there's more details to it, but this is the essence of it. And it seems to violate common sense, right? Well, for example, here we have two objects, a pink pen and a yellow pen. I hold them up. I don't see them attracting each other. Newton tells me they do attract each other, but I don't see that happening. I don't feel it happening. These are not like two magnets which you can feel pushing or pulling. Okay, these are two objects in my hands. Newton tells me they attract one another, but I don't feel that. Not only that, but Newton also insisted that this force of attraction, this attractive gravity thing, works even in a vacuum. Now, a vacuum, friends, is just a space where there's nothing. So suppose we sucked all the air out of this room. That'd be bad. I need to put on, a breathing thing or something. I would suffocate if I didn't. But let's say we sucked all the air out. He would say that the attraction between these two pins, the yellow and the pink, still occurs through empty space, through absolutely empty space. Gravity still operates. And he was right. But nobody understood how that worked. It was very revolutionary. It was mind-blowing. It got philosophers like really angry. The idea of gravity. Let's look at it in a bit more detail. Let's say we've got a pink object here, say a pink planet here. There's my pink planet. People are out there talking. Here's my yellow planet. Okay? There's my two planets. What Newton's telling us is that even in a perfect vacuum, there is a force of the pink on the yellow, and there's a force of the yellow back on the pink. This is, of course, an action-reaction pair from Newton's third law. But this happens through empty space. And it's happening right now between these two pins in the studio. The reason why we can't detect it in the studio between these two pins is that gravity is a very weak force. You need to have very large objects before it becomes very obvious. So the gravitational force between these two pins is real, but it's so weak that all of their forces, including my, the force of my hand on them, is millions of times stronger. So we don't even notice the tiny attraction. But if I were to take these two pins out into outer space and release them, they would visibly, after a few minutes, after half an hour, you would see them start to drift together if there were no other forces acting on them, and it wouldn't take very long before they actually connected. And then they would sit like that forever. unless you come up and give them a good whack. So the force is real. It happens even through a vacuum. Let's say these two planets here are a distance r apart. So r might be, you know, 1,000,000 miles, might be whatever, might be 1,000,000 feet, doesn't matter, at some distance r. And let's say that the pink planet has mass mp and the yellow planet has mass my. And let's take a moment to talk about that term, mass. Sometimes here on Earth we get confused between mass and weight, but they're not the same. Mass is the amount, this is the most simple way I can write it, the amount of stuff in a thing. Amount of stuff in a thing. In other words, this pin, for example, has a certain number of protons and neutrons and other ons that make it up. Right? It's got a certain amount of stuff in there. Okay? And that doesn't change, whether I have it on the Earth or I take it to the moon. Right? The number of ons, neutrons, protons, etc. in this pin does not change when I move it from the Earth to the moon. But its weight does change. Here on Earth it weighs about 6 times more than it weighs on the moon. Okay? The weight changes. In outer space this pin weighs nothing. Okay? On the Earth it weighs maybe, you know, 1/15 of a pound or something. On the moon it would weigh 1/6 of that. Okay, so if you weigh 120 pounds on the Earth and then you go to the moon, you're going to weigh 20 pounds on the moon. You take your bathroom scale, look at it, 120 pounds. You go up to the moon with the same bathroom scale, you put it down, you're going to read 20 pounds. But your mass is the same. The amount of stuff in you, you're still you. Okay, so the mass doesn't change. Okay, does not change. But weight does change as you move around the solar system. I would weigh more on Jupiter than I weigh on Earth. I would weigh less on the moon than I weigh on Earth. Okay? So the larger, the more massive the planet is, typically the more I'm going to weigh. Typically. So mass is measured in kilograms. That's going to be the unit we're going to use. Now sometimes here on the planet we talk about kilograms as weight. In Europe they do that, but technically kilograms is a unit of mass and not of weight. Okay? Pounds is our unit of weight. Kilograms is a unit of mass, and that's what we're going to use in this class, kilogram. I don't have this pin probably has a mass of about 0.2 of a kilogram. Maybe even 1/10 of a, say 1/10 of a kilogram. 10 of these pins would have a mass of a kilogram. Okay, to get an idea. So this is 100 grams. Okay, 100 grams is the same as 1/10 of a kilogram. Okay, so that's mass, and that's our unit of mass. Okay, so what Isaac proposed is that this force F is proportional to the mass of the pink pin, the mass of the yellow pin. Okay, and we'll say more. There's more to this, but let's stop with that. If we take the mass of the pink pin multiplied by the mass of the yellow pin, the force is proportional to that. All that means is that if we double, say, the mass of the pin, of the pink pin, the force doubles. If we double MP and MY, if we make the mass of the pink pin twice what it was, we make the mass of the yellow pin twice what it was, then the force increases to a factor of 4 times bigger than it was, because we have 2 here and we have 2 there. Okay, proportional to means simply this: if the force is proportional to mass, if I double the mass of a single pin, I double the force. If I cut the mass of a single pin in half, I cut the force in half. Proportional to. It's proportional to both the mass of the pink pin and the mass of the yellow pin equally. It's proportional to their product. That's MP times MY. But it is inversely proportional to R squared. All you need to know about that is this. The further apart the two planets get, the weaker the force is. The closer they get, the stronger the force is. So as they come closer and closer together, these forces, as R gets smaller and smaller and smaller, that's what happens right when they come close together. As R gets smaller, the force gets bigger. Basically, here's the clip and save. The larger the masses, the more the force. The smaller the distance R, the greater the force. If you make mass big, you make the force big. If you make the distance small, you make the force big. Okay? The distance and the force, one goes up, the other goes down. One goes down, the other goes up. Force and distance. Distance gets big, force gets small. Distance gets small, force gets big. Force is directly proportional to MP and MY. So if either mass gets big or both of them get big, the force gets big. So these two planets close together have a larger force between them than if they were far apart. And these two planets with the masses they have a greater force than if they had half that mass for each one. Okay? That's what Newton told us. And it has been proven to be correct over and over again. I'll draw one more quick picture in this video. As a planet orbits the sun, say there's our dear beloved Earth, and there's our dear beloved sun. This force of the Earth, of the sun on the Earth goes this way. The force of the Earth on the sun goes that way. Okay, so they're equal and opposite forces. They're always attractive. The forces are always attractive. So as the Earth goes around the sun, there's nothing pushing it around. It's just its inertia. Nothing is making it go around, pushing from behind. The only thing that's happening is it's being pulled towards the middle by the sun all the time. Okay? And we'll get back to that picture in just a minute, but I want you to also remember that the sun is being pulled toward the Earth. But the effect on the sun is far less because the sun is so much more massive than the Earth. Okay? The Earth is very light has a very little mass compared to the sun. So it's affected more dramatically by that force. So the Earth goes around the sun. Okay, here's your clip and save right there. Okay? And also, do remember, the mass is the amount of stuff in the thing, and that does not change as it moves around the universe. Weight changes.